To see how the physics of optics actually works, we have to look closely at the secrets of light. This is Neo the light chaser, the secret of refraction and rainbows. Meet Neo. He is currently in a zero-gravity sprint, tracking a high-speed beam of red watercolor light across this wool felt floor. The chase hits a dead end when the beam slams into a solid wall of clay. This material is completely impenetrable, and it doesn't budge an inch. When light hits a hard, smooth surface, it bounces perfectly off the boundary. We call this the law of reflection. There is a specific geometric rule here. The angle at which light hits the surface is exactly equal to the angle it bounces away. This symmetry makes light predictable. As long as it cannot penetrate a material, it will always follow this reflected path. But the rules change when the light beam enters a material it can actually pass through, like this floating sphere of soft clay. Look at Neo's glove through the sphere. The image shifts the moment it enters the clay, making the hand look severed and disjointed. This explains the distortion. Light travels at different speeds depending on the material's density. In dense clay, the waves slow down and compress. That sudden speed drop forces the light's trajectory to bend, which is the process of refraction. You can feel the physics of it. Just as the thick clay provides physical resistance to Neo's movement, it drags on the light itself. Visual distortion in transparent materials provides a direct, measurable map of light hitting that resistance and altering its course. We can control this bending by changing the shape of the material. In this maze of curved glass, the boundaries are no longer flat. A convex mirror curves outward, altering the path of light to drastically magnify Neo's reflection. A concave mirror curves inward, spreading the light rays out. This makes Neo look small, but it pulls a much wider view of the room into the reflection. Instead of bouncing light off a mirror, we can pass it through a curved transparent material, like this massive convex lens. The curve of the lens forces incoming rays to converge into a single dot. This gathers light from a large area and focuses it into one high-energy point. By engineering these curves, we can harness dispersed light and concentrate its energy into a powerful focal point. Next, we find a suspended water drop in a darkened void, a complex environment for light to navigate. A beam of white light strikes the sphere, piercing the outer shell. Hitting the internal wall at a shallow angle, the light cannot escape. It bounces inside repeatedly. This is total internal reflection. It ricochets until striking the edge at a steep angle, finally punching through to the outside. A spherical object acts like an internal pinball machine, bouncing the light and priming it for a final transformation. A solid beam of white light is actually a bundle containing every individual color of the spectrum. Because each color travels at a slightly different speed, the extreme bending that occurs when exiting the water drop forces the colors to split. This is dispersion. The white beam unravels, cascading into a massive waterfall of distinct watercolor hues that fill the entire space. Neo is now fully immersed in the zero-gravity current of these separated colors. The rainbow occurs when reflection, refraction, and dispersion work together to separate the components of a single light beam, turning a simple drop of water into a demonstration of optical physics.